Alright, this is our second video in 11.1. We just did a couple of connections on the front page and in the first two examples to what is called a derivative, although we didn't really refer to it as a derivative yet, and the instantaneous velocity, if you are given position and time, and also the slope of a tangent line. So I'm just going to go back to that front page here real quick if I can find it. There it is. So this is a little bit nicer than the one I had written on in the video, but we connected the change in y or change in x to finding the instantaneous velocity and using limits to avoid zero division, because we can't put 3 into this thing. The reason why we'd like to is because we'd like these x values to be the same thing, so we're finding the slope at a single point. But we can't do that unless we use limits and we let t approach 3. And with a little bit of math and some simplifying, we were able to do that, and we found out that in this case the ball is traveling 6 feet per second here, which is the same as the tangent slope of the tangent line at that point. We came down here then and did kind of a very similar problem. What we're going to do now in this video is look at, actually I'm just going to use this one that I have here. Okay, we're going to look at the derivative of a function at some value x equals a. So that's really what we did in the last problem, because the derivative is just another word for slope of the tangent line, or in certain cases, instantaneous velocity. And we're going to do it at a point A. Well, in the first example, we did it at 3. In the second example, we did it at 1. Here's a new notation for us, f prime a, or the derivative of the function f at a. And here's how we find that derivative. Sorry. To find the derivative of the function f at a, we find the limit as x approaches a of f of x minus f of a over x minus a. Well, if you look at what we did in our first example, I have to move a few things around here. It's exactly what we did in our first example. I can't quite get it on there. It's really what we did right here. Okay, here's our f of x minus f of a. Well, a is 3 in this case, so f of a is 3 squared over x minus a. Well, in our case, we're using t instead of x, and here's our x minus a. So we really have used this formula already. Okay, this is going to help us compute it at a point A. Now, another formula that represents the same idea, that we are letting x approach a value a so that these both become the same thing down there. We want this to become a, so whatever value you're interested in finding the derivative at, you want that to become that value so that this is going to become a 0 down here. Well, we need limits to do that. Another way that we can say that is we want this value down here to become 0. The distance between the two x values to become 0. And that's what this is saying. Let h approach 0. You may remember in the last video I said we've got this little graph of, I can't find it here, hold on one second. Got this little graph that shows finding the average velocity is from a to b and from f of a to f of b with our y values. We're looking for this distance to close down and become 0. We're looking for this b to get closer and closer to a. So we're looking for this distance. If we want to call this distance h, we're trying to get this to become 0. Trying to get these to become the same point. That's what's happening in this function right here. Geometrically, we talked about this in the last page. This is the slope of the tangent line at that point, a comma f of a. So these are going to give us the same end result. And we really could use these in similar cases. And sometimes I'll use this one, sometimes I'll use this one. And I think as we go through, you'll find which one you feel more comfortable with. I really don't care which one you guys use. I tend to use this one a little bit more because I think this is what you're going to see a little bit more in calculus. So we got a little section here about differentiability. Basically, to be differentiable at a point, you have to have a slope at that point, a defined slope at that point. So these are three examples that are differentiable functions at certain places, but none of these three are differentiable at 0. This one does not have a well-defined slope at 0. I could draw all sorts of tangent lines at that point. This one, the tangent line at this point, is actually a vertical line. And we know that a vertical line has no slope. The slope does not exist for a vertical line. It's undefined. So this is not differentiable at 0. This is kind of like the first example where, since this is discontinuous here, I really don't have any one single tangent line that I could draw here to find the slope of. So none of these three functions are differentiable at x equals 0. Now they're differentiable in other places. For example, if we wanted to differentiate this function at 2, for example, I would just have to find the slope of that tangent line right there. So it's differentiable at 2, but it's not differentiable at 0. That's just one example. All right, so I'm going to end up using kind of an already filled out notes for this first example here, because I think that the colors are actually kind of helpful. So here's what we're going to do. We're just going to cover this guy up so we're not bothered by what's going on over there. And we're going to talk about finding the derivative of a function at 4. This is just like the example we did on the front side where we found the slope of the tangent line at 3. This is our a value. This time it's 4. In our other example, this was y equals x squared, or s equals t squared. Now it's 2x squared minus 3. So we know what 2x squared minus 3 looks like as a function. 2x squared minus 3 is a parabola that opens up. So here's 1, 2, 3, and so here's our vertex, and it's got an a value of 1, so my first point would be, excuse me, an a value of 2. Let me write this here, so 2x squared minus 3. A value 2, so instead of going over 1 up 1, I'm going to go over 1 up 2. Instead of over 2 up 4, I'm going to go over 2 up 8, and so on and so forth. So this thing is going to be a pretty narrow parabola like this. Okay. Now if we zoomed in, or zoomed out actually a little bit more, okay, there's this parabola zoomed out a little bit. There's negative 3 right there. We're looking for what is the derivative at 4. That's what we're looking for here. So somewhere up here is a point, and we want to find the slope of the tangent line at that point up there. Okay, well here's the deal. We know what this y value is because we just put 4 into this function. We know that this y value, if you put this in, 4 squared is 16 times 2 is 32. 32 minus 3 is 29. So this y value is 29. Keep that in mind because that number is going to pop up in our problem later, and I want you to know where that's coming from. It's just the value of this function at 4. All right, so let's take a look at what's going on in our problem here. So we're going to use the computational function with h in it, and I just rewrote it here, except notice that instead of a plus h and f of a right here, like it had in our formula, okay, instead of the a and the a, we know that our value a is 4. So this is what our function is going to start out looking at. So here's what this means. And I'm trying to, these colors, I didn't do a very good job. This is blue and this is green. All right, in fact, it's kind of matching up with the colors that are up here. Nope, just kidding. It's going to match up with the ones that are down here. So we want to find f of 4 plus h. And then we want to find f of 4. We want to find the difference between those. And then we are dividing this by h because that is going to approach 0. And think about it. If h is approaching 0, these are both f of 4 up here too. So we really are finding the instantaneous, the slope of the line that is tangent at that exact point. So if we put 4 plus h in, this is where you might need to pause the video at some point here so that you can really soak in what's happening here. If you put 4 plus h in for x, right there, you have 2, and then x is squared. So here's your 2, 4 plus h squared, and you have minus 3. So this whole blue thing is coming from this guy right here, just by putting 4 plus h in for x. And I mentioned this in class today. Probably a better way to handle this is to use h plus 4 because, you know, it's commutative. You can flip that around, and we're more often than not, we FOIL things out like that. So if you FOIL that out, you're going to get h squared plus 8h plus 16, just from this right here. And that's what you're going to see down here. Okay. Now, you also have the 2. You have the minus 3. Okay, and I kept these blue here. Now, this is important. And somebody had asked me about this after class today. Why doesn't, because they had forgotten these parentheses of what it came down to, why can't you combine this minus 3 here with the value here, and you get a different value other than the 29 or what's going on here? You have to group this together because this is separate from this here. So this is that 29 that I spoke about before. We know that when we put 4 into the function, we're going to get 29. So I kind of talked about that before, kind of showed it there being calculated. So we know kind of where this comes from. What we're going to look for now is what this all simplifies to. So if you distribute the 2 next, and then we're going to have, so 2h squared plus 16h plus 32, and then we're going to have a minus 3. So you have that 32 from bringing the 2 in, minus 3 is 29. So those two 29s cancel out right there. Not doing a very good job of keeping that covered, am I? Those two 29s cancel, and all the terms that we're left with have h's in them. So we can pull the h out, and I'm showing a lot of steps here because I want you to see what's going on. Pull the h's out, they cancel out, and we are finally left with a function here, 2h plus 16, that we can finally put 0 into. So if we put 0 in here for h, remember you're putting this in for h, that cancels out, you're left with 16. So we know that the slope of the tangent line at 4 is 16. All right, so I'm going to stop there, and we're going to move on to the derivative of a function in our next video.